Welcome back. In this video, we'll look at a simple example to understand the concepts and reasoning behind inelastic collisions. If you find this easy to follow, do check out my previous videos for more foundational explanations. Alright, let's consider an example. Let's look at a collision between a bullet and a wooden block. A 250-gram bullet traveling at 200 meters per second collides with a 20-kilogram wooden block moving in the same direction at 5 meters per second. After the collision, the bullet penetrates the wooden block over a time interval of 20 milliseconds. The bullet does not pass through the block. It comes to rest within it after a certain distance, and the combined mass then moves together as one object. We need to determine the final velocity of the block with the bullet embedded in it, and the distance the bullet travels within the block during this time interval. Alright, how shall we go about tackling this problem? For momentum to change, there must be an external force acting on the system. So as long as there is no external force, the total momentum remains constant. This means that whether the collision is elastic or inelastic, the momentum remains constant. Now, you might ask, when the bullet penetrates the block, isn't there a force acting on the bullet? When we consider the bullet and the block together as a single system, these internal forces cancel out. Therefore, they do not affect the total momentum of the system. Another way to look at this is through the motion of the center of mass. Since there is no external force acting on the system, the center of mass continues to move with constant velocity, according to Newton's first law. So both before and after the collision, the motion of the center of mass remains unchanged. Now, if a force is applied to a system, the rate of change of its momentum is equal to that force, according to Newton's second law. So, based on this reasoning, we can now write the expression for the conservation of momentum. Alright, let's plug in the given values and determine the velocity of the block with the bullet embedded in it. This gives the velocity of the composite block as 7.4 meters per second. Now, why can't we use conservation of energy to calculate the velocity of the composite block? Isn't energy conserved? Well, the total energy of the system is indeed conserved. According to the principles of thermodynamics, energy cannot be created or destroyed. However, in an inelastic collision, some of the mechanical energy is converted into other forms that we cannot easily account for. For example, energy may be transformed into heat, sound, or deformation of the objects, especially when they stick together as one body. In this case, some energy is used to allow the bullet to penetrate the wooden block. This energy is not available as kinetic energy after the collision. That is why we say that mechanical energy is not conserved, or more precisely, kinetic energy is not conserved in inelastic collisions. Just to clarify this point, let's work out the mechanical energy of the system before and after the collision. First, let's apply the expression for kinetic energy and calculate the energy before the collision. This is given as 5,250 joules. Next, we calculate the kinetic energy after the collision, which is 554 joules. From the difference, we can see that the amount of energy lost during the collision is 4,695 joules. This energy is used by the bullet during penetration to do work against resistive forces and is dissipated as heat, sound, and deformation during the impact. These forms of energy are difficult to quantify precisely. That is why conservation of kinetic energy does not apply to inelastic collisions. Having understood the energy loss, let's return to the previous section, where we calculated the velocity of the composite block to determine the penetration depth of the bullet. To determine this depth, we analyze the motion of the bullet relative to the block. Why relative motion? Because the penetration depth depends on how far the bullet moves within the block. By considering motion relative to the block, we eliminate the overall motion of the system and focus only on the bullet's motion with respect to the block, thereby simplifying the calculation. We begin by calculating the displacements of the bullet and the block in the ground frame, and then determine the penetration depth using their relative displacement. Before entering the block, the bullet has a velocity of 200 meters per second. During the interaction, its velocity decreases to the common velocity of 7.4 meters per second over a time interval of 20 milliseconds. Assuming uniform deceleration, we take the average velocity of the bullet to calculate its displacement as 2.074 meters. The block has an initial velocity of 5 meters per second and accelerates to 7.4 meters per second over the same time interval of 20 milliseconds. Using its average velocity, we find the displacement of the block to be 0.124 meters. Now, to determine the penetration depth, we subtract the displacement of the block from the displacement of the bullet. In other words, we calculate the displacement of the bullet relative to the block. This gives the penetration depth as 1.95 meters.
Before we continue, I'd like to kindly ask you to give this video a thumbs up, subscribe to the channel, and hit the notification bell so you don't miss any updates. Your support truly means a lot. Thank you. Now, let's get back to the video.
This approach is visually clear and can be understood without difficulty. However, by considering the relative motion, we can directly determine how far the bullet travels within the block before coming to rest. This corresponds to analyzing the motion in the frame of reference of the block. In this frame, we observe the bullet's motion relative to the block. Here, the distance traveled by the bullet directly gives the penetration depth. This is because once the bullet enters the block, it continues to move with respect to the block and eventually comes to rest within a short time interval of 20 milliseconds. To calculate the velocity of the bullet relative to the wooden block, we use the relation for relative velocity. This gives the velocity of the bullet relative to the block as 195 meters per second. Since the bullet decelerates uniformly, from 195 meters per second to 0 meters per second, we use the average velocity to determine the distance traveled during the 20 milliseconds. This gives the penetration depth as 1.95 meters. Both approaches yield the same result. However, by considering the motion in the block's frame of reference, we arrive at the answer more directly and with fewer steps. That brings us to the end of this example. I hope you've gained some fresh insights into inelastic collisions and the fundamentals of conservation of momentum and mechanical energy. Perhaps even a perspective you hadn't considered before. More importantly, I hope you found it both informative and practical. If you haven't subscribed yet, I'd really appreciate your support. Just hit that subscribe button. Don't forget to like this video and share it with others who might find it useful. I'd also love to hear your thoughts, so feel free to drop a comment below. Until we meet again in another video, take care and goodbye.